In this video, I will discuss Euler's method as our first numerical algorithm or numerical method for solving ordinary differential equations or initial value problems. Now, Euler's method is attributed to Leonhard Euler, who invented it in the 18th century. And it is the most simple technique for the numerical solution of an ordinary differential equation or an initial value problem. And it adheres to this form of writing down the numerical method as follows. So here this first line is rather straightforward. This means that we partition the x-axis onto discrete points xi, which are spaced apart with a width of h. But more interestingly is this second formula over here, which says that the solution, the numerical solution in step I plus 1 is equal to the numerical solution in step I plus the interval width or the step h multiplied with a slope. Now, Euler's method comes in two standard variations or two flavors, as you will. And the first one is explicit Euler. And you see that in explicit Euler, well, this slope is simply substituted as the function, so the right-hand side of this ordinary differential equation, evaluated at xi and yi, the current numerical approximation for the exact solution at step I. So by plugging these in, well, you see that based on this ODE, this is a good approximation for the slope of the, or the derivative of the solution to the ODE. So that's explicit Euler because, well, this gives us an explicit equation, an explicit formula for the approximation of the solution in step I plus 1. There's also implicit Euler. And in implicit Euler, well, the difference is that this function, this slope over here, it's, well, again, simply f, but evaluated at xi plus 1. And that's not really a problem because that's something we can pre-compute. This partitioning of the x-axis is something we can do beforehand. But this f is also evaluated at the numerical solution in step I plus 1. And if we are at step I, this numerical solution in step I plus 1 is not known at that point. So this does not give us an explicit formula for yi plus 1, but this will lead us to an implicit equation for yi plus 1. So we still have to solve this thing over here to obtain yi plus 1. And now in the general case, when f is a nonlinear function, you cannot really do this by hand. If f is a complicated function, then we will have to solve that equation, that nonlinear equation, using numerical methods as we discussed in chapter 3. But first, let's discuss explicit Euler, and after that we will go into implicit Euler later on. So explicit Euler, or also called forward Euler, is a very intuitive method from my point of view. So what you actually do is, and you can look at it on this figure over here, is, well, we use the current slope of the direction field. So we use tangent lines at the current point in order to extrapolate the solution over a distance h to the new step. So assuming, let's say that at step I, we are on the exact solution, so on the curve for the function y of x, what we do is we evaluate the tangent to the exact solution. So that is the derivative of y with respect to x. And then we see where we draw the tangent line to our point here, and we check what is the value of this tangent line for x is xi plus 1. So that is graphically what explicit Euler does. Now this tangent line can easily be evaluated because, well, this tangent line has a slope of dy dx, so the first derivative of our function y. And, well, in a first order initial value problem, this first derivative is simply given by the right-hand side of your ordinary differential equation. So that's simply the function f evaluated at the point xi and yi. So that is what's happening graphically over here. And you can see that this gives a approximation. So this numerical solution is an approximation to the exact solution. And also note that if the true solution were a linear function, so a straight line, that we would actually be exact. But in a general case, we are not exact, and we should choose h to be rather small, such that this is a good approximation. Now, in addition to this intuitive derivation, let's say, that we saw in the previous slide, we can also recover the explicit Euler formula from numerical integration. So starting from this original ordinary differential equation that we have over here, dy dx is a known function of x and y. Well, what we can do is we can integrate both sides from the current step, from x is xi, so at the current step I, to the next step, I plus 1. So and that's what we do. We integrate both sides from xi to xi plus 1, left and right hand side. And we see that here on the left, well, we have an integral of dy dx multiplied with dx from xi to xi plus 1. You can easily work this out, and this thing on the left here, well, that will be y at I plus 1 minus y at I. So this numerical solutions at step I plus 1 and step I. The right-hand side is a bit less trivial over here because that requires us to integrate this function f, which could be a complicated function. So working this out, well, this is y at I plus 1 minus yi. We can push the yi, which is a known value in step I. We can push it to the other sides. And this gives us a equation for the numerical solution at step I plus 1. And so we see that here we still have this integral, which we can then proceed to approximate using one of our numerical integration rules. And if we use the left rectangle rule to approximate this integral, this means that we evaluate this integrand at the starting point of the integration interval, so at xi with corresponding yi, then this integral simply becomes that function value multiplied with the width of the integration interval, which is equal to h. So this becomes y at step I plus 1 is equal to y at step I plus h times the right-hand side of the ordinary differential equation evaluated at xi and yi. So this gives you a somewhat more mathematically rigorous derivation of the explicit Euler formula, but I think it's somewhat more important to also keep in the back of your mind this graphical and geometrical, intuitive way that we derived this formula. Now, in addition to a derivation from numerical integration, we could also derive explicit Euler formula from numerical differentiation. And, well, that starts from this original ODE that we will evaluate at step I, so at xi and yi, which leads us to this. So this right-hand side is then the function evaluated at xi and yi. And then what we do is we approximate this derivative over here using a forward difference, finite difference approximation. So in doing so, well, we see that this turns into a finite difference in y values and a finite difference in x values. This difference in x values, well, that's simply by definition h. And in terms of y values, here we have y at I plus 1 minus y at step I. Plugging this back into our original ordinary differential equation, well, we obtain the following, that yi plus 1 minus yi divided by h is f, or reworking this a bit, we can get again a explicit formula for y at time step I plus 1. Let's take a look at an example for explicit Euler. So explicit Euler, we want to solve this initial value problem from x is 0 until x is equal to 2. Now, the specific ODE that we want to solve is the following. So we have that the first derivative of y with respect to x is x times y. So this is our function f. And we have an initial condition here. This initial condition tells us that the function that we're looking for when evaluated at x is 0 should equal 1. Well, again, we can find the analytical solution for this problem, and that is that, well, this gives as an analytical solution through separation of variables, for instance, you can find that the function y is e to the power x squared over 2 satisfies this initial value problem. And you can verify this by taking the derivative here. So far, so good. Let's take a look at what happens when we try to solve this not analytically, but numerically using explicit Euler. And in explicit Euler, well, we again reiterate these formulas here. So we partition the x-axis up until points which are equally spaced with h, and we update the sequential updates of the solution that we obtain are by the following rule. So we update the solution in step I plus 1 from the solution in step I plus h times the slope evaluated at xi and yi. Okay, so let's apply this now. And well, we take a step width of 0.4. So that means that we come up with a total of 6 points divided over the interval from 0 to 2. And well, you see that the values for xi are as follows. So we have 0, 0.4, 0.8, 1.2, and 1.6, and 2. And well, at these discrete points, let's first look at what the analytical solution would be at these points. So that's kind of the goal that we're targeting, that we're aiming for. And we can simply evaluate this function at these specific points. And then what comes out is these numerical values, which are the exact solution evaluated at the specific points that we're looking at. Now let's take a look at what explicit Euler would do for this example. So we start with our first point, I is equal to 1. And now for I equal to 1, well, we simply start at the initial point in the interval, so xi is equal to 0. And we have a pre-specified initial condition. So we know that the exact solution is that the function that we're looking for, so y, at 0 should be equal to 1. So we can simply plug that into our numerical solution as well. And that's what we do. So here we have already a first step, xi is 0, yi is 1. That's our first step. Now, in order to go to step 2, well, we have to update our approximation to the solution. So our numerical solution, we have to update it following this explicit Euler formula. So we use f evaluated at xi and yi as a slope in order to update our numerical solution. Now evaluating f for xi is 0 and yi is 1, well, that's f is x times I, so that's 0 times 1. So f evaluated in those points is equal to 0. We update the solution, so we multiply this 0 with h, that remains 0, and we add that to the current numerical solution, which will give us the solution in the next step, which obviously is also equal to 1. So now we're in step 2. again, what we want to do is we evaluate the function for xi and yi. So this will become 0.4 times 1 is equal to 0.4. We multiply this value for the function or this slope with the step width of 0.4. So that will be 0.16, which we add to the current solution in order to get the solution in the next step. So that's what we obtain here, 1.16. And we keep on doing this. So we evaluate f, 0.8 times 1.16 will be 0.928. We multiply with h and add to the current solution to get an approximation for y at x is 1.2. And that's what we do iteratively until we reach the endpoint of the interval that we want to solve the initial value problem for. And we see here also that, well, we're quite a bit off from the exact solution, but that's mainly because we chose quite a large step here. So if you were to choose a smaller step, and we will see that later, well, we can get closer to the exact solution. Now let's also look at a graphical interpretation of the explicit Euler method. And here I just reiterate the explicit Euler method and what it does. But here on the right-hand side, well, we show for this specific problem the exact solution, which is e to the power x squared over 2. I also plotted the direction field. So this direction field is this function x times y, and I evaluated it at a large number of points, such that you can see what the direction would be that these functions point towards if they pass through these points. And we will also look at the explicit Euler numerical solution points in orange over here. So let's walk through the explicit Euler algorithm. So starting with I is equal to 1, we have our initial condition. The initial condition, which is exact. So at our first point is at the exact solution where y is equal to 1 and x is equal to 0. Now what we do is we draw a tangent line based on the direction field evaluated at our current numerical solution. So that's what we do. We draw this tangent line. And then we extrapolate this tangent line up until the next point in x, so up until xi plus 1. So x1 was equal to 0. x2 is x1 plus h, where h is equal to 0.4 in this case. So 0.4 is somewhere around here. So that is where we will find our numerical solution in step I plus 1. Okay, and then we just start anew. So what we do is we draw the tangent line from the direction field. So in this orange dot over here, we evaluate f, which gives us the direction field. So that is this the slope of this tangent line. We draw that tangent line. We extrapolate up until x is equal to 0.8. And that is where we say that this is then the numerical solution in the next step. And we continue to do so. So again, here in this orange point, we evaluate f, which gives us the slope of this line here. And then we extrapolate that line up until 0.8 plus 0.4 is 1.2. So our new solution is over here. And we continue doing so until we reach the end interval. Now note that by evaluating this f at point xi, yi, we're not really taking the tangent line to the exact solution, because that would be evaluating at the exact point on this exact curve, which is obviously not known, because if we would have known it by beforehand in a practical problem, then it doesn't really make sense to solve it numerically. So that's also important that, well, this slope that we're using is not the exact slope of the exact solution, But as long as we're close to it, well, it should be a good approximation to that slope. So also here, well, we evaluate the direction field, which gives us a line that we then extrapolate up until the next step, the next interval. So this gives us a graphical view of the explicit Euler solution to this initial value problem for h is equal to 0.4. Now, in the previous slides, we've seen that there are quite some errors present in these numerical solutions to ordinary differential equations, and that this depends on the width that you're taking, the width h of the steps that you're taking in the independent variable, or in this case, the variable x. Now, these total errors, well, as we've seen for all the kind of aspects of computational science before, they consist of both rounding errors and truncation errors. Now in this course, well, in this lecture, we focus on the truncation errors because they tend to be dominant in these kind of applications. And this total or global truncation error that we observe after a certain interval of integrating such an ordinary differential equation, this is due to two contributing factors. Well, the first factor is that we have a local truncation error in one step. So starting from an exact point, an exact value of the function satisfying the ODE, we take a step of a numerical method, in this case explicit Euler, and that's, well, causes us to make an error. That is called the local truncation error. Now, because this is a sequential process, so we do this step by step, ever increasing the independent variable x. When we go from step 2 to step 3, well, where we start is not yet, well, is not anymore the exact solution. So this truncation error that we carry over from step 1 or step 2 will also influence the total error in step 3. So we have kind of a cumulative effect or an accumulation of truncation errors from previous steps. And the total truncation error will be a combination of those two things. Now, in the next slides, I will give some kind of a derivation of how these truncation errors behave for explicit Euler and what kind of order that you can expect. Some parts of this derivation might be a bit fast, but if you want to understand the details a bit more, then I suggest you go through this derivation yourself. It's a bit hard to do this on the slide. But the most important things is the general idea and the outcome, not per se the details of the derivation, as this will also not be asked of you on the exam. But let's give it a go. So let's first start out with the local truncation error. So we have this initial value problem. dy dx is f of x and f of x and y. And equipped with an initial condition here. And let's say that the exact solution is this blue curve over here, and that we had partitioned the x-axis up until these points where x1 is 0, x2 is 0.4, x3 is 0.8, x4 is 1.2. So we have an h of 0.4. And we want to look at how the numerical solutions that we will show in orange deviate from the exact solution whenever we apply explicit Euler. So let's take a first step. So we started from the exact solution, and then we take a first Euler step. And this Euler step, well, it's defined as such. So we have the solution at the previous step. And we add to that, well, h, where h here is 0.4, multiplied with f evaluated at x1, y1 over here. Okay. Now, you see here that we have made an error. So this is an error that we made by taking one step starting from the exact solution. So that is a local truncation error. Let's try to say something about the error here, about the difference between the blue dot and the orange dot over here. Now we can do so by writing out a Taylor series expansion. So we will make a Taylor series expansion of the function y at the point x2 around the point x is x1. And that is as follows. So we can write that y evaluated at x2 is y evaluated at x1 plus h times the first derivative at this point. So the first derivative evaluated here times h plus h squared over 2 times the second derivative evaluated at some point in between 0 and 0.4. So that's this remainder term that we observe in Taylor series. Okay, and note that whenever I talk about exact solutions, I will put them in blue, and when they are numerical approximated solutions, they will be shown in orange. Okay, so let's take a closer look at this Taylor series expansion. So we see here, well, this second term here, well, we have here dy dx evaluated at x1 and y1. So our ODE of the initial value problem, well, that basically simply says that this is equal to the function f, which is a function that is provided to us. That's a known function, evaluated at x1 and y1. So we can rewrite this this into this step. So just substituting this ODE over here. And now, well, we can recognize that the first two terms in the right-hand side of this Taylor series expansion are simply equal to the numerical approximation that we obtain in an explicit Euler formula. So, and that's also what we observe over here. We see that this is equal to y2. So this now allows us to quantify the local truncation error because we have a relationship between the exact value at x2 and our numerical approximation at x2, which is y subscript 2. So this local truncation error is simply the difference between those two things, which is equal to this remainder term. And well, let's leave this second order derivative out of the equation for a short while, but I think the important thing to stress here is that this local truncation error is of second order. So a local truncation error here is of second order for explicit Euler. Let's now move from local truncation error in one single step to a global truncation error that we observe after we've taken multiple steps. So let's proceed from step 2 towards step 3. And now we will see, well, the error will be, let's divide the error into two components. So one component, a local truncation error, so very similar to the analysis that we did in the previous step. So assume that we start from an exact initial condition, that we take one step and observe what the error is. And we also want to quantify the accumulated error. So that is the error that we're making by not starting from the exact solution here, but starting from the numerical solution, which is an approximation. Now, in order to quantify this, let's take two different Euler steps, where the first one is, let's say, a hypothetical Euler step. So that's not the one we do in practice, but assuming that we had started from the exact solution here, that we would have taken an Euler step. So we evaluate the tangent line to the blue curve over here, which is f evaluated at x2 and at the exact solution. And we extrapolate that up until x is 0.8. So this gives us, let's say, this y3 star. So that is this hypothetical Euler step starting from the exact solution at x2. And also, obviously, we define the actual Euler step that we're doing. So starting from our numerical approximation, we evaluate the direction field, so f at x2 and y2. So in this point that I'm pointing at over here. So this will give the slope of this line, and that will lead us to this value for y3. So let's look at these two components of the total truncation error in step 3. And well, let's first take a look at the local truncation error. And the local truncation error, well, that's simply the difference between the exact value and this value that we obtained starting from an exact initial condition from here on. So that's y, the blue y evaluated at x3 minus y3 star. And using a analysis completely analogous to the previous slide, we find that this is something like h squared over 2 times the second derivative of y evaluated somewhere in between 0.4 and 0.8. So that's the local error that we're making over there. And let's also try to say something about the accumulated error. So the accumulated error, that is the difference between the green dot and the orange dot here. And we can simply plug in these expressions for y3 star and for y3 in there. And then we see that this consists of actually two parts. So one part of this accumulated error, this y, the blue, so the exact solution evaluated at x2 minus y subscript 2. So this is only because of the fact that we didn't start from the exact y location over here, and this will obviously affect also the difference in the solution at step 3. But also we have this second contribution over here, which kind of quantifies that the slope of these purple curves that we're drawing over here might also be different, because if f is a function of y as well, then the actual slope that we're drawing from our numerical solution might not be exactly equal to the exact slope of the exact solution. So that's what this term quantifies. And let's try to manipulate these formulas a little bit more, such that we can try to see what happens if we keep on doing more and more steps, and whether this also affects the order of the total truncation error. So here I just reiterate our findings from the previous slide, such that the local truncation error is of second order. The accumulated truncation error could be written as follows. Now we can do some manipulations on this. Well, let's try to write this as follows. So we can apply the mean value theorem to convert this from differences in f to a difference in y's, and then we can take this this factor over here and, well, let's say factor it out, such that we can rewrite this accumulated truncation error as follows. Now summing these two will give us the total truncation error in step 3, and that's what we do over here. And let's also observe that in general, we're not so much interested in the actual value of this truncation error, but more in the absolute value. So let's take absolute values of everything and apply the triangle inequality to obtain the following relationship. So we see here that we have now an upper bound for the total truncation error in step 3. Where this still looks quite complicated, and also this has some things that we might not be able to evaluate easily. So this second derivative of y with respect to x, well, the function y is actually not known, so that's something we don't really know. Also, this partial derivative of the direction field with respect to y is something which might not be easy to compute. But let's make an assumption here. So a first assumption is that, well, let's say that this derivative, the second derivative of y with respect to x, that this can be said to be smaller than a number m, where the number m is, well, some non-infinite constant. It can be large, but it's non-infinite. And let's also say that this derivative of f with respect to y is smaller than some constant c. Well, then we can rewrite this inequality over here into the following inequality. So we have that this upper bound can now be written as follows, where we have m and c to be certain constants. And then let's look at this term over here. So this is the exact value at x2 minus the numerical value at x2. And that is actually simply the local truncation error that we had in going from step 1 to step 2. So we can use some formula which is very close to this to further express this term. So using that, this term is equal to h squared over 2 times a second derivative, but then evaluated in between x1 and x2. Well, we can again use this condition over here and say that this is also smaller than a constant times h squared. So this allows us to conclude, well, it's the details here are a bit less important, but what we find here is that, well, at step 3, we have an upper bound for the total truncation error, which is somewhat of the following form. So we have mh squared times 1 plus h times c plus 1, where m and c are constants. Now we can keep applying this in sequential steps. And again, well, the details are not so important, but in every step, well, you can see that we obtain another one of these terms, and also the exponent here increases up until when we reach a given step I, that we have terms up until a power of I minus 2. And you can see that this is general by also looking at step 3 and step 4. And then we can use some mathematical relationship between functions, between sums of this form that we can then write into kind of a quotient like this. And then we see that we obtain something in the following form. And what is important here is that we have an h that pops up in this denominator. Now this h in the denominator will cancel the second power here in this factor, such that we end up with something which is only proportional to h. So we basically lose this second order accuracy from the local truncation error through this cumulative effect of adding accumulated local truncation errors. We kind of lose this second order behavior, but return to first order in the end. Well, and then you can further manipulate this equation a little bit. Again, it's not very important, but the end outcome here is that we find that in the step I, we observe that we can give an upper bound to the truncation error in that step, which is proportional to h. So that is a first order behavior, and which is also, here we have this exponential function in there. So looking a bit critically at these local and global truncation errors. So the local truncation error can be written as follows. So that is has an upper bound of mh squared, is of second order. The global truncation error there, however, is only first order. So we lose the second order behavior, as I already mentioned. So it's only first order globally explicit Euler, which is not ideal. That's not very accurate. But also important is that we see that the upper bound, so this upper bound, well, it grows exponentially with xi minus x1. So if we integrate this initial value problem over a longer horizon, so we go to larger and larger x, then also this upper bound for the error grows exponentially. So this is something really to keep in the back of your mind whenever you're integrating initial value problems over a long horizon, that you should be aware that truncation errors can really accumulate and get very large. So let's take a look at this kind of behavior of the truncation error in explicit Euler. And what I did here is, well, I have this, we have our acquainted initial value problem that we've studied already in a couple of slides. We have here the exact solution in dark blue. And then I plotted for some values of h. So starting from h is 0.4, such that we have five subintervals or 6 points between 0 and 2. And then every time here I halve h, such that we get a finer and finer approximation, or a finer and finer, let's say, partitioning of the x-axis. And what I have in these columns over here is the truncation error, so the difference between the actual solution and the exact solution, evaluated at x is 0.8, so that's here, and at the end interval at x is equal to 2. So let's look at some observations here, and what we find is that, well, if we look for constant h and we increase x, that this truncation error really kind of explodes. So it's by almost doubling the value of x that we're looking at, our truncation error, well, here it goes up with about a factor of 20, let's say, and here it goes, so it's for almost every age, it goes up with about a factor of 20. So this is really a very strong growth. By just doubling x, the error goes up with a factor 20. So this is not really nice. But also we find that if we look at a single column, that by refining h, well, we can only reduce the truncation error proportionally to h. So by halving h, also we have this truncation error. And that's also not very desirable in a good numerical method. Well, you want second or fourth order accuracy, such that this truncation error goes down very rapidly, but here it's only first order. So this is kind of a qualitative look at how these truncation errors behave in explicit Euler. Now let's also look at an additional example. So an additional initial value problem that we'll be looking at is the following. So it looks very simple. So we have that the derivative of y with respect to x should be minus 4 times y. And we have an initial condition of y evaluated at 0 should be 1. And it's rather straightforward to find the analytical solution here, because it is e to the power minus 4x, and you can easily verify this by taking the derivative and then substituting it into the ODE. But so this is the analytical solution, and we see that this is a very stable analytical solution. So it decays from its initial condition. It has an exponential decay towards y is equal to 0. Now let's take a look at what happens when we apply explicit Euler to this example. So we will take a numerical explicit Euler solution where we use h as 0.4, and we start from our initial condition. So we draw a line which has a slope corresponding to the direction field evaluated at the current solution. So that is this orange line. And then we will find a new solution in the next step to be equal to wherever this line happens to be at x is 0.4. So I guess that's around here where I'm pointing the pointer right now. So it's right here. Okay, so that's the numerical solution at xi is 0.4. And what we then do again, well, we evaluate the direction fields. So we draw this line corresponding to the slope of the direction field. We extrapolate up until x is 0.8, so that will be somewhere around here, I guess. And that's where our new solution lies. We repeat this procedure, so we draw a line, see around x is 1.2, so that will be around here. And we continue to do so until we reach the end of our interval. Now let's see what happens when we increase the width h. So let's say that instead of h is 0.4, we would use h is 0.6. And let me also note that, well, this solution is somewhat oscillatory, but at least it seems to come down to the same asymptote as the exact solution. So let's see what happens if we do not make our numerical solution at h is 0.4, but we take h is 0.6. So we start from the same initial condition, which also results in the same, in a line with the same slope that we draw. So based on f evaluated at this point, we draw this line. And then we extrapolate it up until x is 0.6, so that's around here somewhere, and that's where our new value of the solution will be. So then at 0.6, well, we evaluated the direction field, which will give us this line in this case. We extrapolate up until x is 1.2, so around here, and that's where our new solution will be. And we repeat this procedure until we reach the desired horizon for x. Now, an important observation here is that, well, we seem to run away from the exact solution. So this is very highly undesirable. So this seems to have a diverging approach. So instead of converging to the same asymptote as the exact solution, as the stable exact solution, our numerical solution seems to be unstable. So it seems to go further and further away from the exact solution, which is obviously something we wouldn't want. So this is actually a downside of all explicit methods, that extrapolation based on this current slope, so not taking into account any information from what might happen further downstream, so for larger values of x. So this extrapolation based on the current slope, well, that can cause instabilities if we take large steps. Even though the analytical solution is stable, the numerical solution might grow unboundedly. And we will come back to this in a later discussion on what stability actually is and how we can come up with criteria for h such that we can get stable numerical solutions. Now, this is a major downside of explicit Euler, these stability problems that you might occur. And well, instead of purely extrapolating the solution based on current information, maybe we can try to incorporate some information from the solution already in the new step. And that is what implicit Euler does. So whereas explicit Euler updates the solution solely based on information at point xi, yi, in implicit Euler, what we do is, well, we say, let's evaluate this slope not at step I, but at step I plus 1. And this is what we call implicit Euler, or also backward Euler. Now, looking at this graphically, what we do over here is, well, instead of taking this slope over here as we would do in explicit Euler, sorry, what we try to do is we try to kind of find what the slope is at the solution in the next step, even though we do not know that solution at this point. So we try to approximate that slope and then use that slope in order to update the numerical solution. And this also, this description also kind of highlights the main difficulty in implicit Euler. So what we're doing is we try to approximate the slope at a point that we do not know yet. So that's also kind of the difficulty in implicit Euler, that you cannot explicitly compute the slope. It comes out as a solution of a implicit equation. So that's implicit Euler for you. So this xi plus 1 is xi plus h. That's simply this partitioning of the x-axis. And then our update to the solution is as follows. So we update the numerical solution in the next step as the numerical solution in the current step plus h times f evaluated at step I plus 1. So this gives us an implicit equation for yi plus 1. You cannot generally recast this into an explicit form if f is a nonlinear function. So in order to find yi plus 1 from this implicit Euler equation, what we need to do is, well, we need to solve this equation. And since f can be nonlinear, this is a generally nonlinear equation, which we then have to solve for. We have to find the z for which this equation is equal to 0. And that value for z will then be your new value at yi plus 1. That's your new numerical solution. Now you can solve this nonlinear equation using any of the methods that we've seen in chapter 3. For instance, Newton's method or the secant method, whichever works. Let's now try to also look at a graphical example of implicit Euler for this problematic case where explicit Euler seemed to run into problems whenever we took h to be larger than a certain threshold. So for h is 0.4, we got an oscillatory solution, but at least it seemed to converge to the same asymptote. For h is 0.6, the solution seemed to actually blow up. Now what we will do is, well, instead of applying explicit Euler here, where we update the solution based on the current slope or current information in step I, so that would be drawing this line over here. What we do is, well, we try to find, we try to draw a line such that this line has a slope which is tangent to the direction field at step I plus 1. So what does this mean? And let me try to draw this a bit. So we will take a step in implicit Euler of also 0.6, and that's user input. That's something you decide for yourself. And let's say that 0.6, well, that this is somewhere around here. So this is x is 0.6, and we expect our numerical solution to lie somewhere on this line over here. Well, so that's at x is 0.6, and we hope that it's as close as possible to the exact solution. Now, how do we find actually this solution, or how is this defined through this implicit Euler relationship? Well, this basically says that, well, we update yi plus h times a slope, and the slope is said to be tangent to the direction field at xi plus 1. So what we need to do is we need to find a point, or we need to draw a line such that if we draw a line from our current solution up until x at the next step, that this line will be tangent to the direction field at this next step. And well, yeah, this is obviously an ill-defined problem because well, we do not know the solution, so we have to do a bit of guessing over here. So I would say drawing this line corresponds somewhat to this line over here that I'm drawing right now. Because what we see here is that, well, I drew a line from x1 to x2 such that it is tangent to the direction field over here. This is obviously a bit hard to do, and also to do this numerically, it's not straightforward, and that's exactly the difficulty that you have because of this is an implicit equation. We're trying to draw a line tangent to the slope field where we do not really know what this yi plus 1 is, but we can try to estimate it a bit graphically on this figure over here. And so let me see whether my drawing was somewhat correct. Well, it seems that it actually was. So if we have the following line, so this purple line over here that is drawn, well, it is exactly tangent to the direction field at this point over here. And that's also a major difference in between these explicit and implicit methods. For explicit methods, it was easy to draw this line. Well, we can simply evaluate the direction field at known values. Whereas for implicit Euler, we evaluated the direction field at values which are not really known at this point. So you have to do some guessing in a graphical environment, or you have to solve a nonlinear equation when you're doing this programmatically, as is obviously the case in practice. So then the new solution will be here at this point where this purple line crosses the vertical line with x is 0.6. So that is exactly there. And then starting from this point again, well, we go to x is 1.2. So that's somewhere around here. And we want to draw a line from this point up until x is 1.2, such that that line is tangent to the direction field at x is 1.2. So it turns out to be this line. It's not clearly visible because of the resolution of these arrows, but if we were to draw more arrows, you would see that here at x is 1.2, this line is tangent to the direction field, and then our new solution lies here. And we continue to do so until we reach our desired horizon. So note that, well, here we were able to get a quite nice behavior, so it's not oscillatory, such as our initial explicit Euler for 0.4, and it's also definitely not blowing up for the explicit, like the explicit Euler for h is 0.6. So that's what implicit Euler actually does. It stabilizes. It's a very stable method. We will come back to that later, how stable it is exactly. But the main cost here is that we have to solve a nonlinear equation in every step in order to find the new solution. And yeah, mathematically, it comes down to solving a nonlinear equation. On this figure, it came down to me having to do some guessing as to how to draw this line, because we do not have an explicit equation for the slope nor for the solution in the new time step. And when I say time step, it is I mean new step in x. I say time step because in practice, very often this independent variable is time. Let's apply implicit Euler also to our initial example that we had over here. So where we had this function f of x and y is x times y, and this initial condition y at 0 should be 1. We found this exact solution should be e to the power x squared over 2. Explicit Euler for h is 0.4 gave us this kind of solution. And let's see now what implicit Euler would do in this case. Well, again, we take a step of 0.4. And what we need to do is we need to find, well, we basically try to find where at x is 0.4, if we were to draw a line from this point, where this line would end up if it were to have to be tangent to the direction field. And I would say it's somewhere around here. So that's what we do. Well, you draw that line. So here it is tangent. And that gives you the new solution. And we continue to do so up until we reach the end of the interval. And we see that this is actually overestimating the exact solution a bit. Maybe here I can again try to draw this elusive line that we're trying to find. So here we have x is 1.2, so we go to 1.6, so that has to lie somewhere around this line. And let's see if we draw a line from here up and from x is 1.2 to x is 1.6. Well, then definitely this line, well, if we were to draw it like this is definitely not tangent, so it has to be much higher. So I guess it's somewhere like this. This line should be somewhat like this. And let's see whether we're correct. Indeed, this slope is very high, and the numerical solution will also be quite significantly large. And we continue to do so until we reach over there. So we see that, well, the accuracy of implicit Euler is in cases where explicit Euler is actually working, is definitely not better than explicit Euler per se. And this is also because, and I'm not going to discuss this in detail, but this is also because implicit Euler is a first order method, exactly like explicit Euler. Okay, so this closes up the rather long description of the explicit Euler and implicit Euler methods. Here I just want to reiterate these formulas. So we want to solve this ordinary differential equation, which is also equipped with an initial condition. So we want to solve an initial value problem. And in explicit Euler, what we do is we partition the x-axis, and then what we do is, well, we compute in every step the numerical solution based on the previous numerical solution plus the width of the interval multiplied with the slope or the direction field evaluated at the previous solution. This means that it is a very simple and cheap method. We can explicitly compute the solution at step I plus 1 from the solution at step I. But the downside is that this rather easily becomes unstable for large H. Also, a downside is that it is not very accurate. It's only first order, so the error, the truncation error, the global truncation error that we observe at a specific step is proportional to H. We also discussed implicit Euler, and the main difference here is that instead of evaluating this direction field f at step I, we evaluate it at step I plus 1, which tends to work stabilizing. So we use information from further down the road, let's say, such that our solutions tend to blow up a lot less than we have in explicit Euler, where we do pure extrapolation. In implicit Euler, this incorporation of information from step I plus 1 is very stabilizing, and we will actually prove that later on, that it is unconditionally stable. But it's very expensive. So the fact that we have an implicit equation over here means that we have to solve a nonlinear equation in every time step or in every step in order to obtain this the value of the numerical solution in that step. How this goes programmatically, so how to implement this in MATLAB, that is included in the next video. So you will see that in the next one. But another downside here is that also implicit Euler is only first order accurate. So the truncation error, the global truncation error that we observe at a specific step is proportional to H. So that's a downside there. Now, both of these methods are only first order. Now let's try to think of a way of combining both of these methods such that we can get somewhat higher order of accuracy. And this will lead us to the definition of a modified Euler algorithm, which is the subject of the next video.